Hello, Dr. Caps. I am in the bathroom today because I figured that the collateral damage might not be appreciated if I did this upstairs. So, today we're going to be talking about specific heat capacity, which is the amount of heat required to raise it's the amount of heat required to raise 1 gram of a substance 1 degree Celsius. The reason it's called specific is because it is specific to that substance. So the specific heat capacity of, for example, water is 4.184 joules per gram times our degrees Celsius. And we know that liquids, well, water in particular, has a much, much higher specific heat capacity. So it takes a lot more heat to heat water up. It basically, it's like a trap. It can just absorb a lot of heat. Whereas something like air doesn't have much heat capacity compared to water. So we're going to learn today when we take a balloon and fill it with water and then partly with air, we're going to find out what happens when we take flame to it. So the idea, when you're burning something, there's combustion happening, and there's a lot of heat that's being put out by the flame. And so what I've done is I filled the balloon up to about there, and then I'll put some air into it. So we're about halfway, no, we're about a third of the way full with water. I'm going to do 2 because I want to. But the idea behind this is we're going to see what happens when we take that flame with all that heat, and when we put that flame on the balloon with water on the other side of the balloon, we're going to get a very different result from when we put it up against the balloon with air on the other side of the balloon. That heat has to go somewhere. So it's either going to go through the balloon straight into the water and be absorbed by the water, or it's going to burn the balloon because the air will not be able to absorb as much heat. So if air is on the other side, we're going to expect the balloon to burn, but if we hold it on the other side of where the water is, we would expect that the water will be able to absorb enough very quickly to keep it from the heat from actually getting to the balloon. Okay, ready for the fun part? So you can see where the water level is. You swish it. Right there, we're about a third of the way full. Now, right now, that is so cool. I'll show you what's happening. You can see there's a little bit of burnt happening, but it hasn't popped the balloon yet. This very, very thin film of balloon hasn't popped yet because the water inside is absorbing the heat. Now we'll see what happens when I put it up right next to the part that only has air on the other side of the balloon. That is what happens. So the air just couldn't take much of the heat, and so all the heat went to the balloon and pop. It would be very interesting to see what happened if we had a different, something else with water, but maybe orange juice or something else like that, and see if we could get a time and how long it took to burn through. That would be very fascinating. The specific heat capacity of orange juice is going to be different from that of water. So maybe a second edition we can do that. Check that out. It's scalding the balloon. I can even smell burning rubber. Look at that. But there is no pop. Let's try again where we put it on the other side from where the air is, because the air just can't absorb that heat. It's going to go straight to the actual rubber on the balloon, and we're going to pop. That's awesome. Specific heat capacity and balloons. Have a nice day.